everyone. Welcome to the town hall for the fruit detection puzzle, part of Blitz. We do these town halls every 2 weeks with an aim to have you join an expert live call and go through introduction of the baselines that we've created for the puzzle. In this call, we have the ML engineer Deepam Chakravarti joining us, who is going to take us through the baselines for the fruit detection puzzle. So, before we go through that, and which is the core agenda, I'll just give you a brief overview of what the fruit detection puzzle is about. So fruit detection is the second puzzle that we've launched as part of Blitz. And in this puzzle, the task is very, very simple. You're given an image of a tree which has lots of red apple fruits on it, and you have to create a model that can detect, basically create bounding boxes around each of the apples. I'll hand it off to Deepam, who can take us through the notebook. Deepam, over to you.
Okay, so I hope everyone is able to see my screen. I have the fruit detection puzzle open here, and what we'll do, we'll go to the notebooks and we can open one of the baselines. So I have the baselines open here. We can go to collab and we'll just start talking about them. All right, so about the beginner baseline, again, our goal is that we don't want to just throw a deep learning solution at you. We want to explain you, kind of go through the problem, and so that you get an intuition. And here, what we're doing, we're using traditional computer vision methods, which pre-deep learning era, which was like 10 years ago. These were the kind of solutions that we use. Of course, this is very naive, but it gives a good understanding of the problem. So as you can see, we have these images, and what we want to detect is we want to detect these fruits, which are kind of orange, reddish kind of fruits all in every image. And so how we'll approach the problem is we will, of course, first we'll go through the basic steps. We'll download the data set, and all these things, you don't need to change anything here. Is essentially to look at what the data is. Here we can see, okay, image 000, there's a bunch of image 000s here in the data frame. And these are the bounding box coordinates of those. So basically, if one image has, let's say, 50 fruits, there will be 50 rows of image 000, and we'll have bounding box of that. And the label is, there's only one label, one class, so it's always 0. Right. Going forward, we are visualizing the image here. We're using a library called OpenCV to open the image and just show it here. And we can also draw the boxes. So OpenCV also lets you draw these boxes. There is this function we have defined draw rect, which is essentially just drawing some rectangles. And we are using the coordinates to draw the rectangles. As you can see, the labels are perfect here because we have generated the data set. All right. So going forward, we are looking at, okay, what are the kind of variations in the data that we are seeing? So we can see that, okay, how many, one question might be, okay, per image, how many fruits are there? Or another question might be, what is the approximate size of the fruit? So some of them bigger, some of them smaller. So this is essentially just showing that. And you can play around with this. You can change it. You can even add your own exploration code and not talk about it too much. Okay, so coming to the solution. This is a very simple problem. So we are approaching it in a way where you might have heard of color spaces, where normally images are stored in RGB format with red, green, and blue. So each pixel even in your screen that you're viewing this on, it has essentially every pixel has red, green, and blue values. But we can change it to some other space as well. It's just a simple formula to swap it. So what does HSV mean? HSV means hue, saturation, and value. And these three values, they represent something which is more intuitive for humans. Because like if I show you a particular fruit image, it might not be clear to you what exactly are the red, green, and blue values. You might be able to guess, but here it's much more intuitive. So the scale of hue, it's essentially changes the color. So between 0 and let's say 30, it's sort of green shades, and then 0 to 30 to 60, it's kind of progressing from blue to red, something like that, and it just keeps progressing from 0 to 55. Then saturation, it's about how nice and how sharp the color is. So the saturation is 0. It will be very dull, very grayish. And saturation 255 is like very sharp, deep red color, or any color for that fact. Okay, and then for value, value is actually very simple. It's all about the brightness. So it's almost like average of the three values. And if the brightness is very high, like if the brightness is actually 255, then it will be completely white. And then if the brightness is very low, then it will be close to 0. Okay, so that's about HSV color space. So what we'll do, we'll use this simple function called convert color in OpenCV, and it just transforms this image that we have in RGB space into HSV space. And after that, it's very simple, because we know that our fruits are sort of reddish orangish sort of color. So the hue is actually in a very small range from 9 to 18. And then the saturation is also, it's not like very grayish. It's some decent amount of color is there. So we're picking this range 129 to 255. And then the brightness can vary a lot. So it's actually from 0 to 252, which is basically the entire range almost. So this is the range that we're selecting. And then what we're doing, this HSV image that we just converted, we are checking which pixels, each individual pixel is within this range or not. And then all the three values have to be within this range. And this is the plot of it. So on the left side, we can see, okay, when we apply this in range, what the result of it comes out. And we are applying some denoising method on it to basically remove some things. Now, in a deep learning context, this is very similar to what a deep learning model might be learning inside. It is essentially learning these kind of features, okay, features that map to the fruit and not to other things. And then it also learns how to remove all these noisy things. But here we're doing it explicitly. So we're using this method called erode and dilate to remove the noise. You can see what erode and dilate means. I'll not go into too much detail, but dilate essentially means it will expand something. So if you have this J, basically making it thicker. And then erosion is like, if you think of it like real erosion, it's just eroding and cutting into the structure. Yeah, so we are basically applying a combination of that to remove some of this noise. And once we have done that, then we have these blobs on the image. What we need to do is we want to actually identify this blob is separate from this blob. How will we do that? There's this method called contour detection. So imagine this image. This one here, this is fully connected with each other, like all the white pixels are connected. That's actually one contour. And then this 3 is separate from this one because the white pixels are not connected between 1 and 3. Versus this whole box here, this is all connected. So this is one contour. So there's this simple OpenCV method again to find these contours. And what it's doing is, okay, there's some blob here which is separate from this blob. So this will call this as one fruit. We're just calling this as a fruit. And then this is another fruit. And as you can see, it's not perfect, of course. It has many problems. It's not able to detect all of them, but it's a decent starting point and it gives you an intuition because, again, a deep learning model is more like a black box. You don't get an intuition exactly what it's doing, but it is doing something like this. All right. And then you can just go through this code the same way. It's essentially applying this method that we already put into this evaluation pipeline and then submitting in the correct format. All right, so that's about the beginner baseline. And now I'll move to the advanced baseline. All right, so the advanced baseline is one of the state-of-the-art models for this particular problem, which is object detection. So there is this model called You Only Look Once. So it's a fun name that the author originally came out with. So the idea is you take an image and it predicts in one shot what is the points in the points of the object. So, and this is V5 of it. So I think he came out with it back in 2014 or 15. And this is more a very recent one, something end of 2020 is when this model came out. Okay, so YOLO V5, I'll try to give an intuition of how YOLO works, and then we'll go forward with the specific details of YOLO V5. All right, so what is it doing? As we saw the features in for the fruit detection one, it is essentially doing a similar thing. Let's say we want to detect this dog. What it does, it detects features of a dog. Let's say features of a dog might be, okay, it has whiskers, it has a pointy nose, it has ears that kind of are sharp, things like that. And it looks at whole sections of the image and predicts for this particular box area, is there a good probability that a dog exists there. It predicts this class probability map for that. And it also predicts separately these bounding box confidences. So because for object detection, we need to predict where exactly in the image it is. So it predicts actually the center of the bounding box as well as the width and height of the box. So it predicts these two things. How it does it is basically the power of deep learning. So this is more of a classification problem, and this is a regression problem. You set up your labels in this way, and then the loss function essentially is able to backpropagate and learn, okay, the bounding boxes for a dog will be close to where the real bounding boxes should be. All right, so the backbone of the model is essentially used to be a simpler CNN network. Now it has more specific things that seem to work good for object detection, essentially. So I'll not try to go through it in very much detail, but essentially it's like you have different levels of features. So let's say whiskers are like very small ones. They are a few pixels of features, versus if you look at a face of a dog, that is a lot of pixels. So what you want is features at different levels. You want features at very low levels, which is close to where the input side is. And as you go up the neural network, you're essentially getting a bigger view of the entire space. So this layer, it might have only about a very small window of the image. It's not able to see the entire image at once. So it may be able to see the whiskers of the nose, something like that. Versus this last layer, this is able to see is basically the entire image. So you want different levels of features, and something like this architecture-wise you're able to get better results out of your object detection performance. All right, so let's go forward. Again, this part is essentially the same as the beginner baseline. You download your images and you set things up. Then the data exploration, I'm guessing, yeah, this should be all same. All right, then now what would be different here? How do we use the YOLO model? All right, so this part is again same. Then what we have to do for the YOLO model is there are these two different formats which are very popular in object detection in particular. Is this COCO, full form Common Objects in Context. This is the format in which what we have provided you the labels, and basically a lot, I'd say 90% of all object detection data sets use this format. Versus YOLO, when it was created, it's a historical reason, it used this other format called VOC. So visually common objects, I think that's the name. So they use this format. So it's very simple. This is, you have x min, y min, width and height, and this has x min, y min, x max, y max. So you just have to do this simple transform. Once this is done, you have to save the images in which YOLO expects it. So here YOLO expects particular, let's say you have 50 classes. So it needs a set of class, a file which will tell which class belongs to what. and it needs these annotations in the VOC format. All right, then once these are saved, so you can just go through that part of the code. If you're using YOLO, you do not need to change anything like that. If let's say you take this notebook and you want to apply it to your own problem, what you might need to do is you might already have it in the VOC format, then you don't need to change it. Or let's say you have a different number of classes, then you need to change the class map accordingly. But otherwise, you can use this as a starting point for using the YOLO setup here. All right, then it has some other few extra things. So this YAML file is what the YOLO will finally consume. So you also need to set up, like any deep learning problem, you want to have a separate training and validation setup. If you're doing, let's say, cross validation, you might want to have multiple training and validation folds, which you can just save them here and then accordingly continue building on this. So we just have one separate training and validation. We've already split this out for you. What you can do, you can just, as is being done here, you can just split it and you can run this like this. So we're using the small version of the YOLO model, but you can of course change it to any bigger size. It will consume more GPU space, but that is of course dependent on the problem. And here it's a very simple problem, so the small model will really work well. All right, so what we're doing here, these are a few things which you can change in training time. Essentially, YOLO is such a, like, there have been 5 iterations on it. It is a pretty advanced model at this point. So it's not really recommended that you, if you're just trying to fit a simple object detection pipeline, that you go make specific changes in the code. Of course, if you need to do it, that's a different thing. But it's much simpler to use it more like a high-level API. So that's essentially what we're doing here. We have these setups, and some things can change. Let's say the image size, you can increase the image size if you think that there are very low level features that might get missed if you're resizing your images. Let's say you have medical data, which can be as big as 5,000 by 5,000, and you don't want to resize that to 640. But for a problem like this, 640 is fine. So that's what we're doing. And then these other parameters, like of course batch size or epochs, you might have to tune around and play around with it, as well as the size of the model. Okay, so you run this and it will essentially train for some time. Here, because you're training the small model, it does not take too long. And once it's trained, you can look at these validation ones. So what you want to see is, you want to see that the training loss and the validation loss, like any other deep learning model, here there are multiple losses that are being trained. So for the bounding box, one second. Yeah. So for the bounding box, there's a separate loss. This confidence for confidence for that bounding box has a separate loss, and then the class probability that also has a separate loss. So you can see all of that here, and you want to see some good tracking of both. You don't want to see that the training loss is going down, but the validation loss is going up. Then there's something wrong with your setup. So once you're confident that this is properly trained, you can essentially run your detect thing. What of course needs to be same is this image size or any other parameters that you set up during training, they need to be same. And then this confidence, this is a particular thing where let's say your model, you find out that your model is giving too many false positives. What does that mean? Like, it looks at a leaf and it still predicts that it's a fruit. That means that it told that it's a positive, but it's wrong. So you can increase this confidence. That will reduce the chances of such false positives happening. So you might need to tune this to see where your model is better. But for this problem, we see 0.6 seems to be a very good one. And you can just run it like that. So yeah, that's pretty much it. Once you have this done, you have your all your evaluations, all your test predictions in one file, and you want to submit that to AICROW. All right, so that's the code for that.
Right. Thanks a lot, Deepam. That was incredibly helpful. You can share your comments and any questions you have on the explanation in the comments below, and we'll get back to you. That's majorly about the explanation. Now we'll go back to some core aspects of how this puzzle is actually useful in the real world. So this is a low definition problem of object detection of doing it live on the field. But if you imagine we scale up the problem statement, we can actually use this solution to figure out the yield of a particular crop. You can take photos of the whole fields, and then you can figure out what is the yield per particular tree or per particular plant across the field, and it will help you measure your output. That's majorly about the fruit detection puzzle and the solution. Right. So review classification puzzle. This is also a very interesting puzzle that the Blitz team decided to do this week. It's an unsupervised learning problem. We don't do many of those. So I'll just give a quick overview of what the puzzle is about. This is a natural language processing problem, and the problem statement is we are given reviews of lots of different products and things across the internet, and there are about in total 700 reviews, 500 for train and 200 for test. And your job is to do two things on the reviews. First, figure out its class. We've given 3 classes, and you have to cluster the reviews in 3 different classes. And on top of that, also predict its sentiment, whether it is positive or negative. That's majorly the task. And so you're given lots of reviews as text in a CSV file, and then you have to output their classes. The reason this puzzle is interesting is because it covers a simple method of performing sentiment analysis and clustering. It also gives you a great intuition of how unsupervised learning works. On top of that, also learn the core things of how you work with kind of text, how you read it, and then how you train your model on it to predict its sentiment and do clustering. You'll be using the natural language toolkit library to clean up the corpus, perform tokenization, stop words removal, and train it. So these are all very important aspects of doing any problem around this. You need to tokenize each of the words and figure out how best they map to each other. On top of that, we do stop words removal. We remove words like I, me, you, the, which don't necessarily add a lot of meaning to the particular text that you are going to parse. So we also take you through the process of how you do this and how you employ different libraries to do this. And at the end, we're going to create word embeddings for each review using a particular method called Stanford Flow. And then we're going to learn a model that is able to do this. That's majorly about it. We'll look forward to your solutions to this puzzle.